Have you ever been out on a hike? You look at your map, then you look up at this absolutely massive hill in front of you and think, wait a minute, the map did not prepare me for this. Well, that's what we're here to fix today. We are going to unlock the secret language of maps that tells you exactly what you're getting into. So let's just dive right in. It seems kind of impossible, doesn't it? How do you cram three-dimensional information, like the sheer face of a mountain, onto a completely flat, two-dimensional map? It's a classic problem, but you know what? The solution is brilliantly simple once you know what to look for.
Okay, take a look at this. On one side, you've got a normal aerial photo. It shows us what the town of Owingsville looks like from a plane. Pretty standard. But then you have this topographic map with all these strange squiggly lines. That is where the real story is. That's where all the information about the hills, the valleys, and the steepness is hiding in plain sight.
So how do we bridge this gap, between the real 3D world and our flat 2D map? Well, the answer lies in one single, incredibly powerful tool that map makers have been using for ages. Everybody, meet the contour line. This is the absolute hero of our story today. Every single point along one of these lines is at the exact same height. So think about it. If you were to walk a path that followed a contour line perfectly, you would go uphill or downhill at all, not even a little. You'd be walking on perfectly level ground. This right here is the perfect way to think about it. Imagine a hill is kind of like a loaf of bread, right? And you slice it horizontally, with each slice being perfectly even. Each slice represents a certain elevation. Now, if you looked down from the top and just traced the outline of each slice, bam, you've just made yourself a set of contour lines for a topographic map. It's that simple. Okay, so now we know what contour lines are, but to actually read them, we need to understand a couple more key terms. This is kind of like learning the basic grammar of the map's language. First up, we've got the contour interval. This little piece of information is absolutely crucial, and you'll usually find it tucked away in the map's legend. So, if the contour interval is, let's say, 10 feet, it means that every single time you cross from one line to the next on your map, you are going either 10 feet up or 10 feet down. It's the step size for the whole map. And to give us a starting point, maps use what are called index contours. These are the thicker, bolder lines, and they're labeled with their actual elevation. So you can see right here, there's a line for 700 feet and another for 800 feet. So if you know the interval is, say, 20 feet, you can easily figure out the height of all the little lines in between. They're like anchor points for your eyes. And here it is. This is the single most important rule of all. If the lines are packed tightly together, it means you're gaining a ton of elevation over a really short distance, and that means you're looking at a steep climb. But if the lines are spread way far apart, the terrain is much flatter, much more gradual. Just by looking at the spacing, you can instantly see where the cliffs are and where the gentle meadows are. But you know what? We can do way better than just saying steep or flat. We can actually calculate the exact average slope. And to do that, we're going to use a tool you probably remember, maybe not so fondly from algebra class. That's right, good old rise over run. It's the exact same principle we learned in school. The rise is just our change in elevation, which we can get straight from the contour lines. And the run is the horizontal distance across the ground, which we get from the map's scale. The whole process is just 3 simple steps. First, you count up your elevation change using the contour lines. That's your rise. Second, you use the map's scale bar to measure the real-world distance between your 2 points. That's the run. And third, you just divide the rise by the run. That's it. You've just translated those squiggly lines into a real number that tells you how steep that hill is. All right, enough theory. Let's get our hands dirty and walk through a real-world example. We're going to put these new skills to the test and actually calculate the steepness of a real hillside. Okay, check out this map. Our mission is to figure out the slope from point A, down by the creek, all the way up to point A prime. Now, the first thing we need is the contour interval. In the map legend tells us it's 10 feet. That's the first key piece of our puzzle. All right, step 1, the rise. Point A is sitting right on the 720-foot contour line. To get up to point A, which is on the 820-foot line, we have to cross 10 contour lines. Since each line is a 10-foot step up, well, 10 times 10 is a 100-foot total change in elevation. See? Easy peasy. Now for step 2, the run. So you take a ruler, or even just the edge of a piece of paper, measure the distance between A and A on the map, and then hold that up to the map's scale bar. Doing that gives us a horizontal ground distance of about 0.15 miles. And finally, step 3, we just divide. We take our 100-foot rise and divide it by our 0.15-mile run. And that gives us an average slope of about 667 feet of elevation gain for every mile you walk forward. Now that is a genuinely useful number. But let's put that in perspective. Look over at path B to B prime. Just look at it. You can see the contour lines are packed way tighter. And when we do the math, it totally confirms what our eyes are telling us. The slope there is about 1,000 feet per mile. That's significantly steeper than the path from A to A. This is the power of being able to read the map. So let me ask you, you're standing at the bottom, you're ready to start your climb. Are you going to take the route from A to A, or are you going to tackle the much tougher challenge from B to B? One's a steady, manageable climb. The other is a serious workout. Thanks to the map, the choice is totally yours. So why did we just spend the last few minutes doing high school algebra with maps? Because this is not just some abstract classroom exercise. This is a genuine skill with real-world applications that can make a huge difference. Seriously, knowing how to read slope on a map changes everything. You can plan a hike that's going to be challenging, but not, impossible. You can pick the easiest way to bike up a mountain. You start to see the landscape not just as pretty scenery, but as a series of gradients and elevations. You literally start to understand the world around you in a new, much deeper way. So the next time you pick up a map, don't just see a bunch of squiggly lines. See the shape of the earth. See the valleys, the ridges, and the steep climbs. You now have the key to unlock a three-dimensional world from a flat piece of paper. The only question left is, where are you going to go?